Hello again everyone, welcome back to ptet.chemistry channel. So this is work 2 associated with the states of matter, also known as kinetic particle theory. Basically what happens at the particulate level, considering the states of matter being solid, liquid and gases, which we had covered in the previous lecture tutorials for the same topic. This is the 14 to 16 years old chemistry curriculum. So this is a pure chemistry or single science curriculum suitable for the GCSE, IGCSE or O-level chemistry. Anyway, in these first questions, we have samples of 4 gases and they are released in a room at the same time. So we're given the formula together with the name. You should be able to recognize the name from the formula. You should be able to recognize the formula from the name. These are the kind of thing you have to get used to as I cover in the lecture tutorials, some of the common molecules as well as the names and the formula associated with these things. Hydrogen chloride is HCl, hydrogen sulfide H2S, and nitrogen dioxide, similar to carbon dioxide, but instead of carbon you got nitrogen. The dioxide simply means 2 oxygen. Now this is about the rate of diffusion. As you know, in the syllabus, in the specification, we talk about the rate of diffusion increases as the molecular mass decreases. This is how heavy you are. If you are lighter, that means smaller MR or much lower relative molecular mass. And how do you get relative molecular mass? Well, you need to look at periodic table. Based on the formula, you identify the element and then you count how many atoms you have. You multiply by the relative atomic mass in the periodic table, and that's exactly what we're going to do here. So for the first one, the MR of CO2, from your periodic table, carbon is this element number 6. So it's got 6 on top, it's got 12 at the bottom. 12 at the bottom is your relative atomic mass as labeled in your periodic table of the element. They show for a single atom. Here there is no number on the carbon. That means there's 1 carbon. There is a number 2 on the oxygen. There's 2 oxygens. So I have 1 carbon. Each carbon has a relative atomic mass of 12. MR or relative molecular mass, as stated in the syllabus, as stated in the lecture tutorial, is the sum, is adding up all the relative atomic masses. So I'm adding up with the mass for 2 oxygens. In the periodic table, the oxygen is element number 8. It's got 16 at the bottom. So this is the relative atomic mass for oxygen. I've got 2 oxygen, so I should have 16 plus 16. Or what I could do is 2 times 16. Do that on your calculator. You are going to get 44. And then onto the next one. If you try for all the molecule, HCl. So there's 1 times 1. And then I have 1 chlorine. Each chlorine has a relative atomic mass of 35.5 in your periodic table. That will give me 36.5. This thing, the bracket and bracket, that means multiply them together. These are common mathematical notation, even in your lower secondary mathematics. H2S, based on the formula, I've got 2 hydrogen, I've got 1 sulfur. So I've got the mass for 1 hydrogen is 1, because in the periodic table, you got 1 and 1. This is the relative atomic mass for 1 hydrogen, but here you got 2 hydrogen, so it's 1 times 2, or you could do 2 times 1, it's the same thing. I've got 1 sulfur, each sulfur has a mass of 32, that will give me 34 for my actual MR. The MR of NO2, I've got 1 nitrogen, so 1 times 14. I've got 2 oxygens, so 2 times 16, so 14 times 1 is the same as 1 times 14, plus 2 times 16, I get 46. Remember, you want to diffuse the fastest, so therefore we want the lightest, meaning the smallest MR, the least heaviest. So the smallest MR out of all of these 4, given the formula and the calculation you just did, is going to be option C, the hydrogen sulfide. Number 2, we have nitrogen dioxide, the formula of which is NO2, is a dark brown gas. Property of it is denser than air, so you know it's heavier than air. You have a gas jar, the nitrogen dioxide is on top there, it's denser than air. Air is a mixture, so remember that air is a mixture, even from a lower secondary science. This is around 78% nitrogen, which exists as a molecule like that. And then you got 21% O2, and you got 1% other gases, which include carbon dioxide and a few other gases. Now we know that this was brown in color, and then your A, well, at least your clean A, is going to be colorless. So none of the gases present in natural A is going to be colored, but this is colored. When we remove the glass plate, the heavier or the denser nitrogen dioxide is going to move around, and then the A consisting of these gases is going to move around as well. We are actually talking about diffusion. Diffusion is the random movement of particles in all directions from a region of high concentration. So here you have a lot of these brown gas particles, nitrogen dioxide particles. It's going to go from a region of high concentration to a region of low concentration of NO2 here. But the same thing with A, contains a high proportion or high concentration of these gases. It's going to go from this region to this region of low concentration of A until the concentration become uniform. So those are the three main points that you would associate with a fixed essay on diffusion. Any kind of question on diffusion involve those simple ideas: random movement of particles in all directions from a region of high concentration to a region of low concentration until concentrations become uniform, meaning to say the molecules will mix up and then they will be distributed evenly or uniformly throughout this gas jar when you remove the glass plate. So in terms of the color, we're expecting the color to be, after a long period of time, the color will equilibrate, meaning to say the color will become the same because the particles get distributed throughout, they mix evenly, you get uniform concentration. So it's not going to be dark brown on either position, despite NO2 being denser. We're looking at the color getting slightly lighter because the NO2 particles will have diffused from a region of high concentration to a region of low concentration until, after a long period of time, until concentration become uniform. So uniform concentration, that is the last key point in a diffusion essay. Describe and explain diffusion. That is the expected standard for any year 9 chemistry student all around the world. Question number 3 is similar to what we had done in the lecture tutorial itself. Here we got hydrogen gas. So hydrogen gas exists as molecule H2. So Mr of H2 is just 2 times 1. I've got 2 hydrogen atoms. I've got the mass of 1 hydrogen being 1 from the relative atomic mass. So there's just 2. So hydrogen can diffuse in because this is porous. It allows the gas to go in. It allows the gases in the air, so oxygen, nitrogen, etc. It allows these gases to flow out as well. So Mr of O2 is just 16 times 2 is 32. The Mr of N2 is just 14 times 2, which is 28. So this is lighter, therefore hydrogen diffuses into this area at a faster rate because it is lighter. So this is lighter than air, which consists of oxygen and nitrogen and other gases. But this is 79%, well 78%, and this is around 21%. Okay, so this is lighter than air, so it diffuses faster. If you diffuse faster into this thing, you are going to get more particles inside here. If you started out with same level here, that means the pressure inside is the same as the pressure outside. But since the hydrogen diffuses in, you get more particles inside here. More particles inside here, they push onto the top of this water, and therefore when they push onto the top of this water, this level will go down and this level will go up. That is because there is a change in pressure due to the number of particles. The more particles you have inside, due to the hydrogen being lighter, the Mr you show is smaller than this, diffuses into the through the porous spot inside a bit faster than this could diffuse out. More particles push downward, this get pushed upward. So how will the water level at X change? It will fall. So at X it will fall, and then it will remain at a lower level. That is because for as long as you always get this moving in at a faster rate of diffusion, let me think, over a period of time, okay, so it doesn't remain at a lower level, I beg your pardon, because after a period of time, you're going to get equilibration, meaning to say the number of particles, until uniform concentrations are reached, right, diffusion. This is tricky. C and D is definitely wrong. But what do we expect over a period of time? So after some time, when this goes down, will it go back up again? That is a good question. Well, it has to go back up again because of what we had talked about diffusion in the last questions. So the very last point on diffusions is until concentrations become uniform, until the particles are uniformly distributed. So, uniformly distributed. So that is the idea. So when you have initial mean at the very beginning, you have a certain amount of particles inside here. But then after a long period of time, as a result of diffusion in and the gases diffusing out, until the number of particles eventually would become uniformly distributed, where some of hydrogen we have gotten in, some of these we have gotten out, all through the process of diffusion. So after a period of time, that means, not just initially what you see, it will go back to the original level because you would have the same number of particles inside here eventually, but it will not just be 100% just oxygen, nitrogen. It will also contain a little bit of hydrogen as a result of diffusion. So so it can't be option B there. It has to be option A there, return to X as a result of our definitions of diffusion. So question 4, which gas has the slowest rate of diffusion? We know that the factor for the rate of diffusion comes down to the relative molecular mass, which is going to be the sum of the relative atomic masses, which you can get from the periodic table, but you need the correct formula given the name of these substances, which all of these have given you the formula. We want to be the slowest. The slowest means it's going to be the heaviest substance. Heaviest substance would mean the highest MR. The highest MR or the largest MR is going to be the heaviest. If it is going to be the heaviest, it will diffuse slowest. Well, let's work out the MR. The MR of NH3, I have got one nitrogen here. So there's 1 times 14. In the periodic table, you got 7 on top and 14 at the bottom. They purposely, or they already label it for you. This is relative atomic mass, but it's for one atom at a time. So you only have one nitrogen atom, but you got 3 hydrogen atoms. So you will have 3 times 1, which is the relative atomic mass for one hydrogen atom. So that's 17. If we do the same for CH4, there's 1 times 12, and then 4 times 1, or 1 times 4, I'll get 16. MR of O2. So in the periodic table, what you get is 8 and 16. Remember that this 16 is for one oxygen atom. This is one oxygen atom as shown in the periodic table. There's just 16. However, the formula for oxygen, the oxygen that we are breathing in from the air, it exists as a diatomic molecule, 2 atoms bonded together. So I need to do 2 times 16, which is 32. Now the MR of N2, I've got 2 nitrogen atoms. Just like oxygen, they are diatomic, 2 atoms bonded together. So it's 2 times 14 because this number is for 1 atom of nitrogen. Now, which one is the heaviest? The heaviest is 32, and therefore the answer is C, because the heaviest the molecule is going to be the slowest to move, slowest to diffuse. Number 5, why does neon gas diffuse faster than carbon dioxide? Well, if we know about neons, neon is the 10th element in the periodic table. So I think it's 10th. Let me just have a look in my periodic table. 10 and 20. So 10 is on top, by the way, because that is the atomic number. And then the relative atomic mass is given down there. So this is relative atomic mass. Better label it properly. So relative atomic mass, so it's for one atom. And we know that neon is monatomic, or we call it monoatomic. So that exists as single atom because they are noble gases. So they are in the group 8 that exists as single atoms. That is just 20. But the not AR, because AR is for one atom. MR is for one molecule when you have more than 1 atoms combined together. So you got 1 times 12, which is what we did in the previous questions. And you got 2 times 16 because you get 2 oxygens. Each oxygen has a mass of 16 for the relative atomic mass in the periodic table. So this is lighter than this. This has smaller AR than this. Therefore, this will diffuse faster. Okay, so it is talking about the lower mass that's important. So I will just show you how to do it, but if you see this kind of question, you should be able to read through the options and be able to cross out which one is definitely impossible. Rate of diffusion is to do with how heavy you are, and therefore it's got nothing to do with other facts except for relative atomic or relative molecular mass there. Number 6, so this is about rate of diffusion again. So this is about two gases. Methane is CH4, ethene is C2H4. In the lecture tutorial, in your lesson notes, I've already gone through methane, which is CH4. You got to know formula from there itself. You haven't learned this, you haven't done this yet. However, given the formula, you should be able to do something, which is calculate the MR. So there's 1 carbon and 4 hydrogens. So 1 times 12 plus 4 times 1, that's just 16. And now the MR of C2H4, there is 12 for 1 carbon, and I have 2 carbons, so 12 times 2 plus 4 times 1, so there is 24 plus 4 is 28. So we can see that the MR 28 is heavier than the MR of 16, therefore this will diffuse slower since it is heavier. Okay, so diffuses faster diffusion, so it can move a bit faster, therefore it must have the lower MR. So this is lower MR compared to 28. This is lower, so CH4 is methane is diffuse faster, so not ethene. Alright, so always be ready to mark up on your question or annotate on your question, because your calculations matter for you to understand your own work and not just having to reread the whole question, because there will be a waste of time if you don't remind yourself about little things like this. Okay, well, we know about methane molecules being lighter, so they diffuse faster. And yeah, I mean, that has got to be the answer. It's got nothing to do with this size. It's got nothing to do with size, not to do with size for diffusion, but we are talking about relative molecular mass, which is summing up their relative atomic masses. Number 7, these are just some diagrams. These are diagrams representing what happened to the particles. In this case, these are atoms. These are molecule and atoms. Okay, so we know diffusion is to do with the random movement of particles. So there's your first point, random movement of particles. So we can't see the particle moving, obviously, but then we can see the next thing is from high concentration regions, from a region of high concentrations to a region of low concentrations. And what is very important is until concentrations are uniform, or until the particles are evenly distributed after a long period of time. Okay, so what are we looking at? We are looking at a random movement of particles. So here, this is not just movement, because here in option A, you get reaction, whereas diffusion is just movement of particles. Here you get this thing which exists as 2 black atoms, and now they are combined with a white atom. What you get is you get a chemical reaction. This is not just diffusion, this is a chemical reaction. This is not diffusion there. Here you get black and white together, but now you have white and white and black. This is the opposite of that. So both A and B are chemical reactions and not diffusion. Okay, they are representing a chemical change. There's a change in identity. We'll deal more with these when we come across the next topic on atomic structure. Here you have single atoms. Here you have a lot of this white one, a lot of the black one. Now they become evenly distributed, where they get mixed up. So you have mixing. You get mixing because they're randomly moved, they don't combine, but here they combined. So here you get another chemical reaction or chemical change. So this is not diffusion. Only option C shows diffusion, because they're just mixing of particles, blah blah blah. So here you have a lot of white one. Now it's spread to this side, which doesn't have a lot of the white one. Here you have a lot of the black one. It's spread to the other side where you don't have a lot of the black one. Now they become uniformly distributed. Of course, they are still mixed randomly because of random movement of particles in all directions. 3 points to get 3 or 4 marks on a fixed essay on diffusion. Okay. Question 8, we have a sugar lump in a cup of tea. Now, you want to spread the sugar evenly in the tea. Please note that in this question, they did not say mixing. So you do not say stirring, sorry. You did not stir the spoonful of sugar. You just leave it in the tea itself. You see, there's no spoon. You don't stir it. Okay, if there is no stirring, then how in the world does the tea become sweet? So that means the sugar must have dissolved in it. But then on its own, if you don't stir it, it's going to take some time, but eventually it will dissolve because the tea is hot. Okay, so the first thing that happened is obviously it has to diffuse, or it has to dissolve first. Well, I can tell you melting is definitely wrong, because it's not melting, so the sugar is not turning into the liquid. Okay, the sugar is not becoming a liquid. The sugar is becoming dissolved in the liquid water in the tea, but the sugar is not becoming liquid. That is one very, very common mistake that a lot of students make. Okay, so melting is definitely the wrong answer. So now your job really is to decide which one happened first. Does it diffuse first, or does it dissolve first? Okay, so the moment you added the sugar lump into the tea, it will dissolve first because of the high temperature of the water in the tea itself. So actually it would dissolve first, and when it dissolves, then where the sugar are, it will dissolve around this area. It will get mixed with water around here, so you get a high concentration of sugar at the bottom, but then the sugar particles will diffuse. It will move randomly in all directions from this region of high concentration to the region of low concentrations until the concentration of sugar is evenly distributed throughout. That means without even stirring, your cup of tea will become sweet as a result of the sugar lump dissolving first around these regions, and then it will diffuse outward in all directions. So dissolve first and then diffuse, and not the other way around. Question 9 is a classic diffusion kind of question, where you got cotton wool soaked with, here you have hydrochloric acid. Hydrochloric acid is HCl gas dissolved in water. So it is now a mixture because it's dissolved in water. You get hydrobromic acid, which is HBr aqueous. And you get a blue litmus paper. So blue litmus paper is used to test for acid. So what you get are acids, and whichever come across to this end a bit faster, the blue litmus will turn red in contact with an acid. So blue litmus turns red if acid is present. Okay, in contact with acid, blue litmus will turn red. So which one will turn red faster? The one which turn red faster will be the one where the gas diffuse faster from this end to here. And the gas that diffuse faster, it move faster, will be the lighter gas. So the lighter the gas, meaning lower relative molecular mass based on the formula, okay, will diffuse faster. This is the main factor involving diffusion. So we get the MR of HCl. So the MR of HCl is going to be 1 times 1, because you get 1 hydrogen, and you also get 1 chlorine. Each chlorine has a mass of 35.5 from your periodic table. Now MR of HBr is going to be 1 times 1 for the 1 hydrogen, and then 1 times 80 for the bromine. You have 1 bromine in HBr, so there's going to be 81. We can see that this is lighter than this, therefore HCl will diffuse faster than this. Therefore the time taken for the blue litmus to turn red will be shorter for this one, since HCl diffuse faster, because HCl is lighter than that. All these are part of your answer. Now they want you to use kinetic particle theory. This is the one that I mentioned in the lecture tutorial. A lot of students actually mess this kind of question up because they forgot about kinetic particle theory. You must describe what happens to the particles. It's not what you see, it's what happened at the particulate level that you couldn't see, that you need to try to explain in chemistry. How the gases move through the tubes. So the how thing there is diffusion. Okay, so this is talking about both gases. So the gases, okay, the gas there would diffuse from this end to this end. So we need to describe diffusion for that 2 marks. Explain and describe diffusions. The gases move randomly in all direction. So move randomly in all direction. So that is just diffusion. So I'll just write down the key term. There's diffusion, diffusion. That's our first point. And then our second point is from a region of high concentration. So this kind of essay questions kind of repeat itself, but then, it's just the same idea again and again in a different kind of setting to a region of low concentration. So where you have a lot of the particles, I'm talking about the particles, okay? I should really be talking about the particles rather than the gases, but the gases, the particles are the same thing, to a region of lower concentration until the concentrations become uniform, or until the particles become uniformly distributed. So you can say until concentrations are uniform, or you can choose to say until particles are uniformly distributed, uniformly or evenly distributed. Okay, so these are region of high concentration for the HCl. These are region of high concentration for the HBr. They will diffuse here because high concentration to low concentrations. That's just the definition of diffusion there. I didn't complete my bit there. Particles are uniformly distributed. Now the next thing is why the gases take different times. I kind of already show you the working. They are not asking you which one is faster or slower, so I really did not have to do the calculations. I should really have read the question before wasting my time on that, but it's a good exercise to show you that this is lighter than that. So I could also say that the MR of HCl, based on my calculations, I could show my working again if I want to. Actually, I might as well just show my working down there because I already done it, and these are just the kind of thing that you'll be expected to do in a different kind of structured question. Okay, so if I just show my working there, 1 and 2, and then what can I say? The HCl and HBr have, well, actually I might as well say HBr is lighter than HCl is lighter than HBr, or the other way around, HBr is heavier than HCl. Therefore, HCl diffuses faster. If HCl diffuses faster, it takes shorter time. It takes shorter time to reach to the right hand side, and therefore it takes shorter time for the blue limits to turn red when it's HCl because it diffuses faster, for that 1 mark there. Question 9, the next bit is basically about gas syringe. You fill it with HCl gas. Here you have ATCNQ HCl gas. This is at 20 degrees Celsius. You put in hot water at 50 degrees Celsius. So this is at higher temperature. What do you notice? You haven't allowed the gas to escape because this is a block. Block means it is sealed. Seal means nothing escape. So why in the world does the volume increases? And you can read the volume because these are graduated lines. Graduations, or we call them graduated line, are very important because later on you will learn to use this kind of apparatus to read the volume of gas inside here. Here you see the volume has increased. Okay, so atmospheric pressure doesn't change, so this is at constant pressure. This is to do with the laws of gases, but we need to talk about kinetic particle theory. What happened to the particle? Why the volume increases? For that 2 marks there. So what do we know? At higher temperature, so we need to talk about what happened to the particles. So temperature is defined as the average kinetic energy, a measure of your average kinetic energy of the particle. So when temperature increase, your particles will gain more kinetic energy. The particles, basically the hydrogen chloride particles, will gain more kinetic energy. Kinetic energy is how fast you move. So you move a lot faster at higher temperature. When you gain more kinetic energy, they move faster. They collide with the walls of container. They collide with the walls of the gas syringe. In this case, that is the container. So the gas syringe is the container there. More often. So if you collide with the walls more often, therefore you will apply greater pressure. However, your pressure is not changing. It says in the questions, the atmospheric pressure does not change. So since the atmospheric pressure does not change, so what must happen? the syringe, the gas particles will actually push outward. They push, push, and push as they try to expand, and therefore they occupy greater volume for the syringe. So since the pressure is constant, therefore the gases occupy greater volume in order to keep the pressure constant. So that is essentially, saying the last bit, which is on volume increasing as temperature increasing at constant pressure. Okay, so I think, still have one more page actually. So similar kind of questions where we got cotton wool. This is now with ammonia. Ammonia, there is NH3. Hydrochloric acid, there is HCl. And this is about the formation of a white ring of solid ammonium chloride. So your observations, you see a white solid, you see a white ring, which is actually ammonium chloride product. This is the distance travel. So the ammonia travel a greater distance. That means ammonia for the same time, at the same time, ammonia travel a greater distance. That's because ammonia diffuse faster. So the NH3 diffuses faster than the HCl. And the first question is really asking you to fill in the MR. So, calculating the MR of NH3 is 1 times 14 plus 3 times 1. That is just 17 there. And then MR for HCl is going to be 1 times 1 for the 1 hydrogen. And you got 1 chlorine. Each chlorine has a mass of 35.5. Your MR for HCl is going to be 36.5. So fairly easy and direct there. Now, a lot of writing here. The student makes this conclusion. The rate of diffusion is inversely proportional. So this term, inversely proportional, is a mathematical term. It says it's inversely proportional to the relative molecular mass of each gas. So here, do the measurements obtained in the experiment support this conclusion? This is the first question. Does it or does it not? Explain your reasoning. I'm going to explain my reasoning first. Look at this table. So we know the ammonia travel a greater distance. So from the table, NH3 diffuses a larger distance. It travels a larger distance. Actually, it moves a larger distance. It travels a greater or larger distance, 60 cm. Then HCl, which is 40 cm. In the time given, so in the same time given, so we can see that NH3 diffuses faster than HCl due to lower MR. So the lower the MR, the faster the diffusion. That is what we are saying. The faster is diffusion. Okay, so lower MR for NH3, it travels further, therefore it diffuses faster. So lower MR, faster diffusion, so rate of diffusion increases. That is inversely proportional because this is opposite to that. So that is saying MR decreases. So therefore, rate of diffusion is inversely proportional, meaning 1 over the MR, and that is correct. So therefore, yes, it is inversely proportional. It does support the conclusions based on these explanations, based on this data here. We talk about inversely proportional when we talk about pressure is inversely proportional to the volume of gas. This is Boyle's law. And then it's a term you will have come across in physics as well as mathematics. This is inversely proportional, 1 over something. So yes, it does support that conclusion. So this is the last question, part C in this work. When you repeat the whole thing at lower temperature, so this is temperature and rate of diffusion. So how fast things can diffuse based on temperature. So one similarity, there's number 1, and one difference, there's number 2, between the observations made. So in both experiments, you are still going to react NH3 and HCl, so you will still see a white ring. So definitely you will still see a white ring, there's similarity. But then at a higher temperature, this would diffuse faster, this would diffuse faster. So both of them diffuse faster. So you will still see the ring at the same position. because both of them diffuse faster at higher temperature. So you still see the ring at the same position. However, the time taken for this ring to be seen will be faster because this will diffuse faster, this will diffuse faster. So it takes shorter time for you to see the ring being formed. So in terms of similarity, so the white solid ring is still at the same position because both of them diffuse at the same rate, since both of them will be a faster rate of diffusion. Lower temperature is actually slower rate of diffusion. Okay, but yeah, okay. In terms of difference, what did I say about the difference? The time taken. Okay, so as both gases are diffusing slower, so they're not asking for reason actually. So as both gases diffuse slower at lower temperature, this is experiment B. If both of them diffuse slower, therefore the time taken for the ring to form, the time taken for the ring of white solid to form will be longer. Okay, to form or to be seen or to be observed will be longer, so it takes slightly longer time. So how that makes sense there? You're addressing every part of the questions, and this is about observations. This is not about diffusion. It's just about what do you see. Okay, so that's it really for this work, and thank you for watching. So don't forget to click the button on the bottom right to subscribe to my channel, and do share the channel widely with other people. Follow me at ptet.chemistry across all the popular social media platforms. Thank you for watching. I'll see you in the next tutorial video.